We would like to have 4 speakers presenting the theme of overseas vendors. The first speaker is Mr. Magnus Webering, Chief Technology Officer, Asia Pacific Ericsson. Mr. Webering, please.
Good afternoon, distinguished guests. Great pleasure to be here. Great pleasure to be here in Tokyo and to address the evolution of 5G towards and into 6G. It's a great challenge that we have to make sure that we can really grow the 5G business in the industry and that we can leverage those findings and results and leverage that into a platform that we can use long into the next decade as perhaps named 6G. So where are we today in the industry? Well, you have 3 pillars here. Let's look first on the left-hand side. 5G is increasing at a pace that is faster than any previous generation. At the end of last year, we predicted Ericsson we had some 1.6 billion subscriptions on 5G. And the coverage build-out, where 5G services is available, is faster than what we've ever seen before. We estimate around 40% population coverage. Well, that's a half full glass. Let's look at a half empty glass. 1.6 billion 5G subscriptions relative to over 8 billion subscriptions in total. That's less than 19%. Over 80% to go. Likewise, in terms of coverage, over 60% to go. Well, that's a great challenge, and we need to continue that and build and enhance the 5G networks so that those services are truly available everywhere where people are. I often hear from mobile operators the question, how do we monetize 5G? And it's a great challenge because 5G takes great big steps and unleashes new potentials that is yet unbroken territory in the marketplace. But we like to reach out fully to the right and bloom with 5G driven business. But look at the middle column. There you can see some technological terms, but key 5G steps. At the top, 5G standalone. That is to say you use only 5G when you communicate. Well, it may sound basic, but the fact of matters is that absolutely the vast majority of 5G operators today, they start a 5G communication by going through 4G. That was a fast way to get 5G going. But now we need to move all operators up to 5G standalone. Why is it so important? Well, let's look at the second line, 5G slicing. That is a fundamental step the industry is taking in the 5th generation. It allows to differentiate traffic. And if you don't have 5G standalone, you can't do 5G slicing. You can't do carrier aggregation, etc. So if you as a mobile operator want to be an advanced 5G operator, you need to travel down this column. And as you do that, you will learn to monetize 5G to its full potential. Some operators are very much there. We have great examples in China. We have T-Mobile United States. We have operators in Singtel, Reliance Jio in India. Fantastic example that from the start goes and travels down the middle column here. But still, majority of the world's operators have to embark on this journey as they're pursuing 5G business. And doing that will derive new opportunities. And where we're going is towards what we in Ericsson called differentiated networks. That is to say, mobile operators should be able to offer services with different characteristics. And it is important because in 5G we're addressing not only plain consumer business. We're addressing enterprises, industries, government sectors that step on step, as they digitalize, onboard use cases that require more stringent delivery of the information. One small example, we had a representative here from Germany. In Germany today, it's a car rental company called Vey. When you order a car from them, you're alerted through the app to go out and wait for the car. As you do, the car approaches you on the street, but there's no driver in the car. It is being driven remotely from their offices. Vey personnel sit behind their desk in front of a few screens and drives the cars on the streets of Berlin. Now just imagine, what does that require from the mobile network? It requires differentiated traffic. For that service delivery to be safe and secure, mobile traffic needs to be there. And this is just, I'd say, the start of the beginning of 5G value-added services. So with that example, some other reflections. Is 5G well on the way? Absolutely is. We have good examples on all continents of the world. 3 areas here. You can see on the left-hand side, Far Eastern in Taiwan, doing slicing, 5G slicing in the field. Here they're doing prioritized traffic for first responders. The police force is now trying it out and using it more and more. Fire brigade is starting, and ambulance services is starting as well. It's not hard to motivate when they have an emergency incident that voice and data communication is prioritized. But how we do it implementation-wise in the field, and how then on top of that the operator derives their commercial service, is territory to be set out. Far Eastern is a front runner here as one example. Middle column, going into industry cases, we see a number of key industries, large multinational companies with advanced requirements on wireless connectivity. In particular, I'd say in the car industry, very leading brands are now building factories based on 5G connectivity. And then lastly, an example from medicine. Ericsson started early to talk about remote surgery. It's actually coming about. But another field in medicine that's happening now, a university hospital in Singapore, they've started to use XR, or augmented reality, when they do surgery. So ahead of surgery, they scan the patient and get a 3D picture of it. And as they perform the surgery, they have goggles on, and as they look at the patient, they can overlay information from the scan. And they can actually see the veins of the patient, and thereby, as they cut into the patient, sorry to be explicit, but as they do the surgery, they can ensure that they don't cut veins and waste blood. So you have cutting-edge XR technology that requires high bandwidth, reliable communication. And they said, no way, we're going to do this for Wi-Fi. Security, trust is not there, and capacity is not there. But 5G delivers it, and it's in operation, doing surgery today. It's for real. So if you look on the blue part of this slide, we have a long, challenging time ahead of us to really excel on 5G. A lot more functionality will come in there with new releases from 3GPP and advancing the system more and more. And we will address more and more segments in industry, enterprises, public sector, etc., to digitalize society. As we're doing that, we, the industry, will derive new knowledge. That knowledge will help us to set requirements on what comes beyond that. And therefore, on top of this slide, you can see a purple field gradually building up. And that is what we may call 6G in the future. We have the IMT parts there with IMT 2030 requirements. That is already starting to being worked upon in many groups. But over time, the blue area here will feed up vital information into the purple and make sure what we have 2030 and beyond is something that is potent enough to be relevant in 2040 even. So what are we shooting for? Well, often I get the question, what is 6G and what is the use case for 6G? And I still say I don't know. And more important, I shouldn't know. And that is again because we really have to look here far into the future. But what I know is to qualify technology that perhaps could be ready for mass production in the time frame of 2030. And I also know to study the most demanding use cases today to leverage as much as possible on them into the future. When our research team looks at it, they often talk about a cyber-physical world, to have a step beyond what we think of today. And that is really to connect a digitalized world and the real physical world. And in perspective then on what our industry has done here in the past, if you take a 30-year time span, from a technology point of view, the bit rates, the communication pace has increased by 1 million times. It's a phenomenal increase. And a pillar in that is that, as we heard before, we're addressing a global market with a global technology base, regardless of where different players come and where they play. But the base, as we have in the specifications, is a global set, and that drives scale. So the cyber-physical world, imagine two halves. One is a physical reality that we tend to live in every day. The other one is a digital representation of it. We talk about a digital twin. That's indeed what they already use then in the Singaporean hospital. But as we now look into the future, we go beyond that. We talk about massive twinning, when we can really go back and forth these domains instantaneously with massive amount of data. And if we're going to do that, we need to have a pretty good manager, so to say, in between. That's the networks. That's the mobile networks. While we have representatives from the public side here, what does that imply? Well, spectrum will be sought after in the future. I think the Finnish representative here put it very well: ensure timely securement of new spectrum allocations. That, if anything, will be needed going forward. But also how we aggregate data, regulations for it, and how these operators can aggregate data from different corners of the domain where they operate. It can be inside of national borders, it can be outside of national borders, subject to regulation. So here are 6 areas where potentially we can find and leverage new ideas on where 6G can take a go cross new boundaries. A few years back, Ericsson coined the term Internet of the Senses. Now it's talk more about massive merged reality. But imagine if your communication go beyond your audiovisual communication. We know already in game consoles you can have vibrations to get a better feel. But what if in the future you can feel temperature, maybe smell, maybe feel texture when you do e-shopping? No. Do I know how to solve that? No. But I know we are very qualified engineers who can push the boundaries and see how far can we be to have the solutions 2030 and beyond. We talk a lot about situational awareness, where we can aggregate information and also in both directions gather, essentially bring in and also push out with different rules for who gets to know what, to increase the awareness of what happens around you. Depending on you, who you are, you have different kinds of information. Efficient data, satellite communication, satellite supplementary support to the terrestrial systems is being discussed about a lot today. Okay, great. But where are we? Where should we be 2035? Maybe we should have other mechanisms to ensure that we can leverage on the vast footprint that we have with people all about here and there and having communication devices with them. And then new kinds of devices, perhaps even devices that fit under your skin. Bit interesting thought. But there are medical helps that can be given if you're more connected. So in our work now, we have different categories. You see a few building blocks here looking at the use cases. Internally, I say, let's smoke a bit. Let's see how far we can push the boundaries. AI, machine learning is of everyone's mind, of course. That will be a foundation going forward for how we build support in the networks. Then the enhanced communications that I addressed with the merged reality. Beyond communication is interesting. We can use the networks to do sensing of different forms, and then perhaps the fifth box, even more interesting and a bit new, flexible monetization. So far in the industry, we've had very straightforward. Today, if you look at plans, it's small, medium, large. We need to give mobile operators more tools for that. We took a big step in the industry 2 years ago. We acquired an aggregator, the company Vonage, that aggregates information and makes it easier for developers to access the networks. We're enhancing that now, allowing the operators to, like the Open Gateway in GSMA, expose information from the networks and then have tradable information to the app developers. That's happening in 5G. But of course, we should, at the onset, now think of this for 6G. We should not only have the communication APIs that the industry is talking about so far, we should have information from the network APIs, and then truly go beyond communication in a 6G fashion. And the key thing then is the management of information and data. The network contains a lot of information today which are not traded with applications but can be. One small example is positioning data. But also we foresee in the future that the networks can then have pools of information from other sources which they are allowed under a certain network of rules to be used for the applications. And again, the driving factor here is, of course, to make the applications more potent and more desirable for consumers, enterprises, industries, etc. And of course, increase the monetization possibilities for the mobile operators. So then what is 6G? Well, I said before, I don't know, but we're assessing where to go. And here you can see some pillars that perhaps can be adopted in the industry. And these are thoughts. These are not cast in stone in any way. But there are some principles that I think is worthwhile in the industry to discuss. Can we uphold these, and how should we uphold them in that case? We should absolutely have a mode in 6G where we could go directly to 6G and start the communication, like we have in 5G. Should we, at the very start, go via 5G or not? In the 5G area, we decided to go through 4G to go to 5G. But do we need that in 6G? That needs to be debated. One proposal is to go straight to 6G. Then we need to overlook vital interfaces. Which ones are there? And how do we have the right level of openness? And we've had a large debate on what open interface there should be lately in the industry. I think that's very much set now. But let's have a look from a 3GPP, the standardization group point of view. I think 3GPP today has over 100 open interfaces. Then comes the question, are all of those needed? How many of those interfaces are really used? And let's say we would go down to, pick a number, 90. Is there much of a loss? There's a gain in efficiency, I would argue. But where's the optimal number, though? I don't know. But this, I think, is something where our research engineers in the industry, as they become more concrete, can look at. This is a chance to overlook and see, is this an optimal number, or is there another level we should be at? Radio spectrum we've had addressed here. I think, again, that is be vital. It's very important, I think, that any new spectrum released for 3GPP technology should be, or IMT 2030 technology, should be IMT 2030, should be used by IMT 2030 technologies. Here in Japan, it goes generation-wise. I would encourage Japan and other countries to have all IMT spectrum open for any generation. That provides flexibility for the operator, and they can faster move up to the highest G, which drives innovation in that country. And then I think very important that we saw in the introduction of 5G, the ability to share spectrum on a carrier between the newer G and the older G is very beneficial for the mobile operator. So these are a few cornerstones that I encourage the industry to discuss on how to potentially put some stakes in the ground for 6G. Then on the technology phase, here are 11 areas where we divert interest in and see again, what can we qualify, what is the top notch the industry can do by the end of this decade. Spectrum coexistence is there as an example. What spectrum can be used and how wide bandwidth we can have, fundamental questions. And the industry needs a number of years to understand how far technology can be pushed. Then on the right-hand side, we have zero energy devices. And that's an area that I think is interesting. Can we have new kinds of devices that you don't need to charge every night? Right? And the answer is most likely yes, but they will have some boundary conditions. But our research team is well into it, and together with MIT in the United States, we're doing some very interesting research. On the right-hand side, you see one research team at MIT. They look at fabric, potentially future fabric that can sense pressure. So you have fibers in a lattice that can sense how you're moving, okay? Let's say, we don't know, but let's say this would be commercially viable 2035, let's say. I'm sure there will be many interesting applications. There will be medical applications. One customer once snapped, great, then I can exercise my golf swing. Yeah, there will be many innovations coming. But how do you connect it to the network? Well, not through a cord, right? And you don't want to charge it every night. You don't want to charge your sweater every night. Right? So it just has to be there. And on the left-hand side, you see a prototype, a very early prototype, I should say, that we've done together with MIT on zero energy devices. It's a tiny device, which is very bandwidth limited and cannot communicate very far distances, but say 30 meters. And it operates at very small power levels. But you have a round circular antenna there. And with this antenna, it gets the energy of the radio waves that are always around us. And that energy can be used to transmit back a few bits of data, enough to say something about the movement in this shot. So if this would be a commercial reality in the next decade, you could potentially buy a jacket and then go on the internet and see how you've been moving. Huh? And then looping it back, this can potentially be under the skin of you and measure your heartbeat or some other measurement that your doctor wants to monitor. Do I say this is the way we should go? No, I don't. But I say one thing, is that top-notch researchers at MIT and with the support from us, they're pushing the horizon. They're seeing what could be possible. And later, as we go in standardization phase, we will see what support can we have in the networks for potentially these applications. And later in the marketplace, we'll see how will this come to the market. But it's to exemplify where we are in the industry today. We don't know this is going to happen, but we'll see how much can we push the horizon. And the last example there is something we showcasted last year, not the least then at the World Radio Conference, deciding on future spectrum. We're already having prototype work on how wide we can do different receivers, here addressing the very vital 7 to 15 gigahertz bands. This is pre-commercial, but is to see, again, what can we qualify or what may become into products later on. So I tried to exemplify now a number of initiatives and ideas of where research teams are getting more and more knowledge that later can go into phase for standardization. And then I feel it's appropriate to have this idea of how it can play out in the industry. There's no fixed time plan, but we have some targets. There's an ITU process for the IMT 2030 requirements, where different groups are now gearing up work. I think in the gray area there, we have the regional activities. That is, I argue, great work. We have work here in Japan, we have in Korea, we have in China, we have in India, EU, and the United States. In each region, there are activities, and there's a great deal of crosstalk between these groups, which I argue is very beneficial. It's again a process where we test different ideas and start to harmonize what is more likely to be mature in a few years' time. And then towards the end of this year, next year, very likely activities can start, for instance, in 3DPP, with study items that eventually can be brought forward to the standardization process. But this activity is of course driven by industry consensus, and we will see how that advances. So I think for 5G, we're on to a fantastic start, but it's the end of the beginning. We are entering a very interesting phase for 5G, and that's when we go to truly mass deployment. As a reference, I think India in the last year plus has done a leapfrogging in terms of building up 5G service to a truly good performance, and is now starting on innovating on 5G. That's energy for anyone. Hold hands with India and innovate on 5G. Then in that process, experience will be learned, and that should be fed into the process of defining 6G. The efforts we have so far, I think, are well on track, and with good crosstalk, that I think is a good recipe for continued success. And then eventually, during this year, we start to become more and more focused on how we take the relevant steps into the big standardization groups. And parallel to this, we saw here from Korea 2026 and onwards, I think many others will agree on that, is a good time frame. We also need to be out in the field and do real measurements and feed that knowledge back into what goes in the standards. And that's the standards then that will go beyond 5G. Thank you very much for your attention.
Thank you very much, Mr. Wavring. では、ここで質疑応答のお時間とさせていただきます。ご質問のある方は、その場で挙手をお願いいたします。スタッフがマイクをお持ちいたします。ご質問は、日本語でも英語でもどちらでも結構でございます。Now we will proceed with the Q&A session. If you have any questions, please raise your hand and our staff will bring you a microphone. Either in English or Japanese is fine. Questions? No questions? Okay. それではマイクをお持ちいたします。2列目の方です。
Yeah, thank you very much, Magnus. I'm just using English to ask a question. In your talk, the key part of your talk is focused on the cyber-physical connection for the future. Then we also mentioned about the monetizing for the future operators. So how do you draw a link between these two? Because it seems like one is catering more for end users, and the other one is, like I say, his corporate business viewpoint to see the services. Thank you.
Yeah, thank you. Very good question. And very straight. I wish I knew, right? but I think it's this is a good challenge we have in the industry. I think the cyber-physical view here is more on the technology base, right? We believe if we can fulfill this vision of really mapping or sensing what's in the physical world, bring it over to digital world, analyze it, bring it back, get new information back and go back and forth, we will be able to derive more value for whoever has used this service based on that. But how that service will be offered, how will be monetized and so on, you know, we need lots of right people to think there, and we can turn around. It's a great area for innovation, if you wish. Then I think if somebody wants to innovate on it today, great, think of it, I'd say. But the real battle is in maybe 7, 8 years when it hits the marketplace, right? But I think with any technology introduction like this, my motto is always be out early. Because when you're out early with a new technology and test it in the marketplace, you get early feedback from consumers. And there will be a phase there where, or users, I should say, can be enterprises, where you need to find out what's the best proposition for them. If we just have a reflection on the journey with 3G, 4G, let's say with mature 4G today, we talk about the app community. The industry has had an enormous learning cycle from 2005 to 2020. Today we take it for granted of having smartphones full of apps and the economical system on top of that. So that was not invented overnight. I guess something similar here. But the ones who has a chance to win are the ones who are in it early and try to shape it and understand it early.
Okay.
Yeah, thank you very much. And by the way, my name is Mitch Zheng. I'm with E3 from Taiwan. And so based on what you say, it's like I said, right now we need to encourage the 5G operators, just do it. So that we can get a start early and then we can get it first.
Yep.
Thank you.
Yes, I agree.
Thank you very much. So, anything else? Questions? Oh, okay. Keep phrase, please. では一番前の方です。
Thank you very much, Magnus. I'm Aki Nakao at the University of Tokyo. So thank you very much for your great talk. And you said this is end of the beginning for the journey to beyond 5G. And I think it's true because in several years now we have to start doing a pre-standardization, and then maybe we should talk about standardization. As a global vendor, Ericsson, have you already identified the key technologies for 6G, or what we should be doing for the next couple of years, because we are running out of time? And if you want to share your outlook towards the standardization of 6G technologies, please share.
Mm-hmm. Well, thank you, Professor Nakawa. So I think in the process of standardizing a new generation, what we've seen in the past is that I think the success is we've had a forum, 3GPP, where industry players from all over the world with the intent of driving the next generation have been there and under the rules and terms of that forum discussing on a very free ground and together qualifying what are the merits for certain proposals and then taking the step to go ahead with it. I've been asked that kind of question before, and sometimes I get the ask, Ericsson is so big in it and so on. I say, well, we've been good at having an impact. I humbly acknowledge that. But I say that it's in a way it's very frustrating to work in it also because nobody controls it. There's so many entities, so you have to be a good citizen in the community, so to say, and find solutions that are good for the industry. And I think we can go through specs and see you have contributions from such a wide group of industries from all parts of the world. And that makes it's technology-wise very sound, and it's also very well accepted. So that's the strength we have. Now your question was also, what should we do next? I think we are in a good state. In the slide I had with the proposed timeline, where we have the regional initiatives that over some period of time now have worked locally and written white papers. I know there's been exchange between the groups. When I look at white papers from different groups, there's a lot of commonality in terms of roughly where it's going, right? Not individual proposals, but the overall direction. And that, I think, is a good base now to start over this year and next year to identify study items. And now I talk in terms of how 3GPP has done it. I think that's a good proposal. Then that process will qualify different proposals and then based on the outcome of that, do the standardization work. That's proven good in the past, so I think it's one strong candidate.
Thank you very much. We put a lot of things, a lot of technologies in the white paper, and now we have to start thinking about, we have to agree on some identify promising technologies for the use cases that you mentioned. And I think we are running out of time, so I think I agree that we should start now.
Yep, thank you.
Thank you very much. 他にございますでしょうか? Anything else? Questions? Okay. No questions? それでは以上で質疑応答終了とさせていただきます。This concludes the Q&A session. Thank you very much, Mr. Werbering. The next speaker is Mr. Wen Tong, CTO, Wireless Huawei Technologies. Mr. Tong, please.
Good afternoon, everyone. The title of my talk is Entering the AI Era with 6G. In this talk, I will focus on AI and 6G and the impact of recent AI revolution to the development of 6G. With the rise of a large AI model technology, we are entering an AI era, and we are in the midst of an AI revolution. We can predict that in 5 to 10 years, 90% of research and development work, the design work, and almost all the text work will be replaced by AI. This trend will intercept the time window of 6G deployment. In the internet era, web technology became the platform. Google, Facebook, Twitter, and Uber were born and built on the web software-based platform. The era of mobile broadband, the mobile technology, namely the LTE technology and 5G, become the platform for the smartphone app. And we do almost everything on app and MBB platform today. Now we are in the, what is the platform for the upcoming AI era? It will be not the app, it will not be the web technology, it will be the AI agent. AI agent will be the platform for the future service and applications. At the same time, the success of a large AI model will put AI agent on an unprecedented higher intelligence level. The next AI deployment and development will not be only the generative AI as we know today, it will be the interactive AI. Such an interactive model is the AI agent, and the AI agent is a meta-intelligent entity that can sense, can recognize, can reasoning, and can make decisions and take actions. Furthermore, AI agent can autonomously set the goals and can perform self-learning to acquire the physical world knowledge and to perform self-improvement continuously. Even furthermore, in 6G, the network will enable the so-called AGI, the Artificial General Intelligence. As early as 2019, we set up the connected intelligence as the ground vision for 6G. Here we mean 6G for AGI and AGI for 6G. In this context and the background of AI breakthroughs, last June, ITUR completed the work on the definition and the framework of 6G. That is the answer of the question, what is 6G? There are two parts of this framework. The first part is the continued evolution of the connectivity capabilities, such as mobile broadband, high reliable low latency communications, and massive machine type of communications. While the second part is the novel part of 6G. It is the first time that ITU definition of the mobile technology with the new capability that beyond the connectivity. They are integrated sensing and communication, integrated AI and communication, integrated terrestrial and non-terrestrial networking. We are very excited to see that the ITU 6G vision become a global consensus. We have seen many researchers' activity to apply the AI technology to enhance the connectivity capabilities, such as to enhance the immersive communications, to enhance the extreme communications, and to enhance the massive machine type of communications, to enhance the NTN, and even to enhance the sensing. But the key topic for today, my talk, is the AI, 6G for AI. It is how to design 6G to natively support AI, AI service, AI application. For example, how to design EMBB Plus and ULLC Plus and MMTC Plus to better support AI services, how to make 6G relevant to AI, to become an integral part of AI, to become a part of AI training and AI inferencing. In the case of people-to-people communication, people-to-machine communication, and machine-to-machine communications, the 6G network, 6G UE, are enabled by AI agent. Here, 6G AI RAN can further embrace 4 basic capabilities of an AI agent. That is a sensing, recognition, decision, and action. Since this is an architecture with beyond the connectivity capabilities, we call this a goal-oriented architecture. In other words, 6G AI RAN will understand the intent and take the action to interact physical world and digital world. With the ChatGPT as an example, the large language model in the near future will surpass the human level of intelligence in some areas. However, to run such a model, we need a huge computing power to provide the human level of intelligence that is the human-like AI agent. As of today, we need many megawatts power to power up the training of a model with 500 billions of parameters. Even for 10 years later, it is not feasible to run such an AI agent on mobile handheld device to deliver the AI service to everyone, everything, and at anywhere and anytime. In this chart, we show the 6G so-called C plus A plus S networks and the devices with the AI agent at the cloud, AI agent at the edge, and the AI agent at the device to realize the vision of connected intelligence. This is the complete picture of a post-Shannon communication schema. The first type is the people-to-people communication for the machine learning is the most challenge problem. The second is the machine-to-machine communication for machine learning. We can claim that we achieved breakthrough and it will have massive application in terms of a potential market. The third part is the people-to-machine communication. This is done by 5G URLC type of technology to perform the human tactile internet with interaction with the physical world. The fourth type is the machine-to-human communication. This is, in fact, the metaverse communication. For machine learning, this is a generative AI. In 6G, the AGI communication will become the so-called, based on the so-called river effectiveness communication. We can simply call it intent communication. This is the framework that is beyond the Shannon paradigm. The Shannon architecture is about transmission of bits. However, bits cannot represent intent. Bits cannot represent understanding, and the bits cannot represent intelligence. This is the fundamental difference for 6G AI communications. As we can see for the 6G AI AGI to AGI communication model as shown in this chart, the inner channel is the Shannon channel, and the outer channel is the large AI communication model for the large to the other large AI model. Next, we talk about native AI capability for 6G. This is the most impactful, even perhaps the revolutionary way for this capability is its potential to become a new communication architecture, as I mentioned, since the machine learning is the part of a communication. It adds intelligence, since machine can learn. So the learnable part of the communication can be made much more effective. And for example, in the case of a 6G people-to-people communication, for each individual, we can create a deep learning model for system one. Such a model will be perpetually updated in digital world as a digital twin for the red person and blue person. And to communicate, we first apply the inference computing on the system one digital twin of the party on each side. If the digital twin cannot provide a satisfied answer, then we use 6G, for example, EMBB channel in the physical world to communicate so-called system 2 intelligence. As time goes by, system 1 digital twin can be almost complete, represent these people, and therefore lesser bandwidth will be needed or required. The second area of 6G is integrated sensing and communication. The straightforward usage is to apply sensing to assist the communication. The sensing will explore much more detailed side information for the communication channels and even to reconstruct the entire real-world environment for optimization of the connectivity. Typically, the integrated sensing and communication at the centimeter and the millimeter frequency bands are represented by point cloud. We can use point cloud and the data set and to apply the signal processing, especially here we use the deep learning neural network to represent 3D model. Our goal is to restore the true physical world, and we can call this as somehow the radio rendering even. This is the network side of the integrated sensing and communication example. The 6G integrated sensing and communication will be more useful on the device side, especially for the 2B application. Here, the concept is to use 6G, for example, the terahertz integrated sensing module. Let's call it the ISEC T-Hertz, embedded on the robot, and to use the ISEC T-Hertz sensing capability to scan the environment, to retrieve the image and measure the depth and position of all the objects around. And in this mode, the ISEC terahertz is served as a terahertz camera. And all the ISEC terahertz model are exchanged, the sensing information are shared among themselves. In the complementary, we can also add, in addition to install some optical wireless integrated sensing and communication devices capabilities as a fixed infrastructure, and the optical camera as a sensing and optical transmission to share the optical sensing data. One of the tasks of the ISEC optical wireless is to gain the high precision measurement of the physical objects. Furthermore, we can perform the data fusion computing for the terahertz and optical wireless. In this way, we have 6G enabled. We will need the 6G enabled D2D connectivity and the mutual sensing, multi-view sensing, and to perform the computing and control of the robots to jointly to do the collaborative tasks. Now, this is the 2B side and the 2B and the device side. The next key idea is to use 6G ISEC chip and machine learning to emulate the behavior model of the robots. In other words, to use 6G ISEC to replace all type of sensors. For the 2C cases, our proposal is to use the 6G ISEC in many cases. There are many ISEC chips could be put on the robot. Our goal is to create a general purpose robot for consumer market, that is for everyone. In fact, the general purpose robot is a dumb robot. However, it has an AI brain. In other words, it is lean on the robot side and it is heavy on the network side or AI computing side. At the genesis time, the robot has a little intelligence. The human workers start to teach the robot to do the real work tasks. The human operation is treated as a ground truth for the deep learning neural network learning. Now, the AI brain can learn 24 hours a day and 7 days a week as long as they have the 6G connectivity. More specifically, 6G eMBB is used for the virtual reality, and 6G URLC is for the transmission of the command to perform the physical world action. The AI model can be more dynamic with the orchestration. Here, we actually operate the robots to construct the AI model to further expand the orchestration of multi-tasks. We summarized the new RAN architecture for the AGI communication in the 6G timeframe. This is a mobile network that can support the communication plus AI plus sensing. We call it ARAN. Similarly, the 6G core network element can be constructed with the AI agent. Every network element can be an AI agent, and the network function can act as an AI agent as well. At this stage, the AI agent is the integration of a large AI model supported by the planning and the toolboxes and memories. And we show the A-core architecture. The blue color part is implemented by software platform, and the red part is executed on the hardware platform. However, the software development and deployment are experiencing a fundamental revolution thanks to the success of large AI model. Here we show the large AI model assisted co-pilot software coding capability. It can further evolve to autopilot-based coding capability, and eventually, very soon, it will become an agent-based software creation, which means human only provide requirement and the agent will do end-to-end complete software creation. The latest OpenAI GPT store is an excellent example. In just 2 weeks or more, the APPs on the GPT store exceeds the total amount of APPs of Apple Store since its creation. As early as 2015, we proposed the so-called application-driven network, the ADN. The central idea of ADN is given the customer applications and requirement, we can automatically create a network to customize for such application. After service of such application is done, the network can retrieve the network. In this way, network platform is just like a computer with the AI agent as a foundational building block. We can realize a core network for 6G. That concludes my talk. Thank you very much.
Thank you very much, Mr. Tong. それではここで質疑応答のお時間とさせていただきます。ご質問のある方はスタッフがマイクをお持ちいたしますので挙手をお願いいたします。ご質問は日本語でも英語でもどちらでも可能です。Now we will have a Q&A session. If you have any questions, please raise your hand and our staff will bring you a microphone. Either in English or Japanese is fine. Questions? どなたかご質問のある方いらっしゃいますでしょうか。いらっしゃいましたら挙手をお願いいたします。No questions? ご質問ございませんか。ではいらっしゃらないようですので、質疑応答のお時間は終了とさせていただきたいと思います。Okay, the Q&A session conclude. Thank you very much, Mr. Tom. The next speaker is Mr. Peter Vedder, President, Bell Labs Core Research, Nokia. Mr. Vedder, please.
Okay, good afternoon. Thank you for inviting me and giving us the opportunity to share with you our vision on 6G. And the title of the talk is 6G Network at the Center, and you will soon understand what I mean by that. Everybody agrees, and the previous talker explained that extensively, AI will really have an enormous impact on technology, on our economy and our society. There are studies that show that it has a productivity growth impact of 1.5% in the next decade, an impact on the GDP of 7 trillion. Everybody also agrees that cloud is essential there, is also a game changer to enable all these AI applications, to store the data, to give access to the AI processing capabilities, to create applications in an agile and scalable way. And then you can do these things that are symbolized by these icons, the Internet of Value, the enablement of blockchain and smart contract for new business models. Industry 5.0, So Industry 4.0 was about industrial automation. Industry 5.0 adds to it the digital twin capability, having a real-time understanding of what's happening in the physical world in order to improve productivity, efficiencies, and also safety. Industry 5.0 also enabling put the human in the loop and let machines or robots or AI do what robots and AI are good at, but also let humans do what humans are best at. Interfacing with these digital twins, we have the industrial metaverse for industrial digital twins, and XR, augmented reality, that allows us to interface with these digital twins and have the best representation so that the humans can act and take complex decisions, problem solving, and then let the AI take it on from there. But then also commercial, consumer metaverse, ability to interact with ourselves and our family, friends, with digital twin models of ourselves, and be in the place as if we were there through holographic representations. And then last but not least, the new API economy. In that future infrastructure, giving easy access to application developers, service providers, through easy to understand application programming and interface, and again, enabling multiple actors to collaborate in new ways and getting a multiplication of the benefits of the AI and cloud infrastructure. But the title of the slide says 3 pillars. The third pillar is really the network. The network is at the center of all this. It provides the connectivity of sensors that update the data in the AI and digital world. It connects back to the humans and to the devices, the decisions and the control. So the 6G network is really at the center to enable the AI and the cloud infrastructure. It's about spectrum that provides the capacity. It's about the performance that is required, the autonomous network operation, generated software creation of network functions as well as of applications, the ubiquitous availability of all that connectivity, the connectivity of the distributed cloud, we could call it a cloud compute continuing, and really have a cloud network fusion, a joint orchestration of resources, giving access to common off-the-shelf compute capabilities, but also then having specialized semiconductors to get, especially in the network, to get to the best performance at the lowest power consumption, and then making that infrastructure also ready for the quantum compute era, to benefit from quantum computing, but also to make it quantum safe to deal with potential security hazards. Surrounding this is a shell of AI that deals and automates all these different functions and capabilities and simplifies it really. Then, and also exposing it to the application and service developers. Very essential also is then creating that in a cyber-secure way, and last but not least, also in a sustainable way. So 3 important pillars. 3 is a charm. Here's another way of looking at this. So there is the artificial intelligence pillar, there is the cloud continuum pillar, but in the third pillar in the middle at the center is really the network. On the AI side, we can enable Net for AI, or AI as a service, and allow such things as AI processing on the edge, if you want that. System 1 thinking at the edge, or System 2 thinking more in the cloud when you need more context or when you need rapid decisions. On the cloud continuum side, it is really about that fusion of cloud and network and co-optimizing the resources, the network resources and the different compute resources, and really leverage that cloud compute continuum across multi-cloud. Underneath that, we then have that network that needs to be crypto-agile for any emerging security threat that there can be. There can be AI threats and quantum threats, as I already explained, quantum computers that can hack encryption code that is deemed safe today, but also AI is a tool that can be used to hack code. AI also as a tool to detect anomalies. So making it crypto-agile so that the network can keep up with new security threats. Then a network with required performance, so we go beyond the 5G capabilities with below 1 millisecond, but that is not required in the entire network. That will be requirements that are contained in special area networks like a machine park or so, where you want 100 microsecond latency, and maybe sub-microsecond synchronicity, hundreds of nanosecond synchronicity. And do that with the highest reliability, 7 nines, 9 nines reliability. And then also the increase of traffic, the increase of capacity by an order of magnitude. And what we cannot allow is that then the power consumption of the network go also up by an order of magnitude. We pledge that we will design networks that in total energy consumption will be 50% lower than today's network. So the energy efficiency should be improved by at least a factor of 20 in this. The traffic growth. Here this figure explains this quite well, what we expect as traffic growth in the current decade. The regular mobile network traffic, but then also what fixed wireless access adds to it and what the advent of mixed reality adds to it. And what we clearly see that is already by the mid of the decade, we are running out of capacity with the installed base of 5G. So today there's about 25% installed base of 5G. Continuing further 5G installation up to 80% penetration. Also that by the end of the decade, that capacity will run out of steam and will no longer support the traffic that is needed for the coming decade. So even if you don't believe in a new use case for 6G, I'm saying there are, but even if it's just traffic growth, you will need new capacity in new spectrum, and hence you need new technology that provides that high capacity with the best energy efficiency possible. So what are these applications that we are going forward? They're not starting from scratch. We are already working on this today. For instance, we have 4K video that is evolving through mixed reality video in 5G Advanced, preparing us really for the 6G era where we expect to have holographic representations. Also in digital twinning, that is already happening today in very specialized applications like digital twins of jet engines or so. And we start already seeing, and we have a development project around that, developing digital twins of, for instance, vertical farms, of warehouses, or factories. In the 6G era, digital twins really go at a broader scale. Think of digital twins of harbors, of smart cities, where you have multiple actors that want to benefit from a shared digital twin infrastructure, where you have multiple actors that provide input to that digital twin in a safe and secure way. And then at the bottom, another example, the network already today has data that can be valuable for the applications. There are traffic patterns, and all such information. Then in 5G Advanced, we can already enable localization, 5G positioning. In 6G, we will have a network that we, pun intended, call a network with a sixth sense that provides additional sensing capabilities that and I'll speak about that in a minute, that we leverage the network infrastructure also as a sensing capability, as an additional modality to give that accurate update of those digital twins of the world. So value creation in 6G, is it evolutionary or revolutionary? It's actually both. There will be current application, and this is a map, and don't try to read this map. This is just to say there's many applications that already are used today and that we can expect in the 6G era to improve in performance, to be deployed at a much larger scale. for instance, for digital twinning, there will be a massive scale of sensors that allow for that accurate digital twin model of the world. And then there's new applications like those very low latency, high reliable, very localized extreme networks, for instance, in the machine park. We, at Bell Labs Consulting, our colleagues have already tried to look at what is the opportunity, what does it really mean for the industry, and then again, the total addressable market, and what does it really then also mean for the communication service providers. And I won't go into the details of this, and this is crystal ball gazing to some extent, educated crystal ball gazing, I should say. And there's also large uncertainties. Those blue bars give you the uncertainty of the total addressable market potential. Just picking the largest one, network real-time digital twins for industries, is an opportunity of about $30 billion US. So we're on this 6G journey to enable that 6G era future already for 5 years. 5 years ago, we started as an industry to define the key technologies for 6G. And we all agreed that there must be 6. That makes it easy to remember. There's maybe not exactly the same 6 research vectors, but there are 6 of them. New spectrum technologies, improving the capacity over new air interfaces. Then using AI, not only for network automation, but also as a new way of creating an air interface. Then using the network not only for communication, but also as a sensor. Then fourth is that extreme connectivity, how to provide those very extreme requirements of 100 microsecond latency, nanosecond synchronicity, reliabilities from 6 to 9 nines, possibly low power consumption. So how to enable these very specialized networks. And then the fifth one, do this in an automated architecture, leveraging the cloud capabilities, and do it and leveraging AI. So a cognitive automated architecture. And then last but not least, do it in a security and trust and privacy preserving way. At the center, you see that leaf. It needs to happen also in a sustainable way. What I will now do is, in those 5 years, we've done quite some progress as a research community, and I'll give you a few examples. And a variant of this slide you have already seen by previous speakers, the new spectrum technology. So you recognize the existing bands, the low band having the widest coverage as explained by the horizontal axis, then the mid band that provides the high capacity, and then this millimeter wave band that was 10 years ago hailed as the 5G technology, but because of its limited coverage, did not really yet see its commercial deployment, because the mid-band really provided the capacity that was required at a much lower deployment cost. So lesson learned for 6G, the industry, well, first of all, we can expect that we repurpose these bands for 6G, but this, as already said, it will not be enough. So we have already identified the 7 to 15 gigahertz band, the upper mid-band, as we call it, or also the golden band for 6G. World Radio Conference has identified that as these are bands that we need to study and have great opportunity for 6G. In the research, we also have attention for the upper, the sub-terahertz range, as we call it, with even shorter coverage than millimeter wave. So we are very careful. This is maybe not the first deployment of 6G, but these research investments already pay off for wireless backhaul. And then if there is an additional capability that we enable with those radios, like the sensing capability at high accuracy, thanks to the wider bands at those higher frequencies, then there is opportunities that we should explore in research. And so at Nokia Bell Labs, we have research in both of these directions. The challenge with the sub-terahertz ranges is really how do you do in a cost-effective way the radio frequency integrated circuits, and also how do you do the packaging? How do you create these antenna systems, these array systems? Because at these frequencies, the classical packaging with organic PCB materials don't really work anymore. The attenuation is just too high, the permittivity is prohibitive. So we're looking at new materials like radio and glass. So that's what you see on the left-hand side. It doesn't look transparent, it's because there is a metal coating on it, but this is a radio substrate that has the appropriate material properties to integrate radio frequency integrated circuits with antenna systems. And these research investments are already important for wireless backhaul to enable 100 gigabit per second for point-to-point over the air, and they are beneficial also for proof of concepts with our sensing systems and potential future mobile access systems. The other one, the upper midband from 7 to 15 gigahertz, is the real focus for 6G for the first deployments. And why is that band so interesting? Well, we have shown in simulations that you can get nearly the same coverage as with the current midband, 3.5 gigahertz. So that makes them amenable to deploy from existing cell sites, and hence that's why the deployment is so much lower cost. But to achieve that coverage, you will need many more antennas in your massive MIMO systems so that you can focus your beams much better to the UE devices and have better signal to noise ratio. Now, fortunately, physics is on our side. In such massive MIMO systems, the antenna spacing is half a wavelength. So if you double the frequency, you get 4 times more antenna elements in such a radio panel. But the physics is not on our side in terms of the electronic processing that you need to do for that massive MIMO. This goes up by the power of 3 of the number of antenna elements. So you really need creative research, new algorithms, new modular system architectures to enable energy efficient deployment of these large-scale massive MIMO systems. And why is that so important? Well, in future radio networks, in future networks at large, 70% of the power consumption is in the radio access network, and most of that is actually at the base station. And so what you want is power consumption, ideally, that follows the traffic load, that you don't have constant power consumption, but there's no traffic or full traffic load. And you can already achieve that with microslots, and you can scale the power consumption of the power amplifier in light blue here. But then there's also digital front end and digital signal processing, the layer 1 processing, as we call it. Now, there's one thing that you can actually do better. It's not linear. You can actually do better than linear, knowing that these high power amplifier outputs you only need when you have the largest simple constellations. If you have lower traffic, you can back off your power. So that exponential is basically, for those people that know Shannon's law, the log function. This is the inverse of the log function of Shannon. But you can do more. You can actually, in your antenna system, mute parts of your panel, and in this way create more energy efficiency. You can do that with the power amplifiers as well as with the digital front end. And if you architect your system well, you can even do that also with your baseband processing. And then there's also innovations in the power amplifier and the digital front ends that get us further power consumption reduction. So there's a lot of things that we can do to improve the energy efficiency of future radio systems. Then the second research vector that we had there was the use of AI in new ways over the air interface. So you see here the classical designs of transmit and receive with these individual functional blocks like synchronization on the receiver side, channel estimation, equalization. And for each of these functional blocks, there's already a large body of research on how you can further optimize that with machine learning. What we have done already several years ago at Bell Labs is the insight that by combining such functions in a single deep neural network, you can actually get better performance. And you can also, there's an opportunity to simplify the AI, because every machine learning has a number of layers. And if you combine, you can reduce the total number of layers. That you can already do in 5G. You don't need a new air interface for that. But when you have a new air interface, you can actually start thinking of a new air interface that allows for a feedback loop between transmitter and the receiver. You can co-optimize a deep learning transmitter with a deep learning receiver. On the transmit side, there's such things that you can do as the waveform learning or the automated beamforming. And we've actually built the first proof of concept using a GPU platform. And we've shown in that proof of concept with this end-to-end native air interface that you can get around 30% improvement in capacity thanks to these native AI air interface approach. The right-hand side is also interesting. It's a self-learned symbol constellation. So people familiar with the radio transmission, you very know quadrature amplitude schemes. They're very symmetrical. The self-learned constellation is actually much more intuitive. If you think of it, this polar constellation is actually more energy efficient for the transmission, and there is an asymmetry there that also gives us better phase information. So actually, it's very smart what these ML machine learning systems can do. And thinking afterwards, yes, right. So this is the AI air interface, and of course power consumption is a concern with the current GPU approach, but we have also active research on how you can further improve the ASICs that can do these kind of AI processes. Then the new capability that we see beyond communication is the sensing, and the idea is you will have in future radio all around you. Using some form of radio arrays that can do beamforming. So you can start thinking that you can scan a room and that you can do radar-like technologies to sense presence of humans and objects. So we're not reinventing radar here. The idea is to reuse the communication system, the OFDM signals, and to also do it in a way that does not impair the quality of service of your communication. You can do more than just localization. As you know, radar can detect also speed. It can detect motion, heart rate, for instance. That object over there is a human or a mammal. Maybe there's a frequency component of a rotating fan. Must be a piece of equipment. And then if you apply AI to the signals, you can learn, for instance, such things as gesture. And you can imagine that then you can do gesture control, command the flight of a drone just by the movement of your arm, for instance. So we have also built the first prototype of such a sensing, joint communication and sensing system. For that, we use a commercial 5G millimeter wave system, 28 gigahertz. We hacked it such that we can detect the back-reflected signals. And we developed algorithms so that the quality of service is not impaired and that we optimize the beamforming for the sensing with optimal resolution. And for those people that have been at Mobile World Congress, we actually had a demonstration there with a very simple use case where, so behind that 6G screen that you see on that picture, there we had our millimeter wave system, and it could detect the distance, and people could walk up and down, and there is a giant piano on the wall, and you could play a tune. Now, that is very gimmicky. The real use cases are, for instance, in industrial automation, that you detect the presence of people and that you can then apply safety measures so that trucks or robots don't hit the people. And we've actually, in the meantime, installed the system also in an experimental factory in Germany, in Stuttgart. To benefit from all these capabilities, we are also envisaging a new 6G architecture, a 6G architecture that is based on a multi-cloud environment with the central cloud, edge cloud, far edge cloud. In between, you have an optical network fabric that provides the necessary capacity and performance to interconnect these data centers. And then you have the access networks with a multiplicity of technologies and multiplicity also of actors. So there's private wireless networks, there's the CSP networks, there's satellite networks. So to deal with all that complexity, we want to create a unified networking experience that I come in a minute. On that infrastructure, you can then, through virtual network functions, microservices, stitch the right services and compose the right network services. And on that same infrastructure, you can then also realize the applications. And the whole idea is that you do that synergistically, applications with the network functions that you're creating and with the infrastructure capabilities through the proper application programming interfaces that shield the complexity, increasingly use large language models to make them really easy to use, and then enable the orchestration, the automation, leveraging the data and the analytics, network digital twins even, and also do that with the proper security and trust. So to make all this happen, this network at the center, we need a network operating system, and we're taking a holistic system approach that really takes into account all the elements that are needed. And we call that future system UNIX, Unified Networking Experience. This is a nod to Unix. Unix, the operating system 50 years ago invented at Bell Labs. And it's really, you want autonomous service creation starting on the left, leveraging the data and knowledge across your network and your applications, leveraging the knowledge of your applications and your service, making network-aware application, making application-aware networking systems, and then leveraging the cloud compute continuum and really have that optimum placements of functionality, and enabling a decentralized environment, an environment where you have multiple actors. So our thesis is the best way to address this is do this in a unified way. So we're on this 6G journey already for 5 years, and also it's very complex. We're embracing the collaborations in the ecosystem. In the US, there is the NSF, National Science Foundation Rings. There is also the NextG Alliance, now gearing up to private-public partnerships. In Europe, we have the 6G Smart Network Services umbrella organization with the many European projects geared to 6G underneath it. In that, we have the flagship project HexaX, now in its second phase, HexaX2. And then we have several regional initiatives in Europe, for example, in Germany, 6G ANA. Also in Asia, Asia Pacific, many initiatives like here in Japan, the IOWN. So 6G is really transitioning. We heard already from previous speakers, standardization is around the corner. We need to put 6G in next gear. We are transitioning from that exploration to what I call the systematization. So the takeaway is really the 6G network will be at the center. It's the essential third pillar next to AI, next to cloud, that really is reshaping the way we do technology, new application, and impact society. Thank you for your attention.
Thank you very much, Mr. Vetter. それではここで質疑応答のお時間とさせていただきます。ご質問のある方、スタッフがマイクをお持ちいたしますので、どうぞ挙手をお願いいたします。Now we will have a Q&A session. If you have any questions, please raise your hand and then our staff will bring you a microphone. Questions? Okay. では前方のお願いいたします。
Thank you, Peter, for a great talk. I actually have lots of questions, but I think I should minimize the number of questions now. So let me ask 2 questions. First, about this upper mid-band frequency, and last WRC 23, so we agree on 7 to 15 gigahertz, but I ask around, Japanese telcos, so they may not be too much excited about, or maybe pretend not to be excited, but in your slides, you said capacity enhancement For that, you plan to use that 7 to 15 gigahertz. But in your talk, you were mentioning that you put a MIMO antenna so that you can make an area. And what exactly that, are you looking, what's the viable use cases for this band? I would like to know that. And are there any telcos excited about this, centimeter wave? So this is my first question.
Yeah, thank you for the question. What we have learned in 5G is if you can deploy higher capacity from an existing cell site, that's what you will do. Even if you have other technologies like 5G millimeter wave that provides even higher capacity but that require deployment of new cell sites. So it is lower cost in deployment as well as in equipment to create a larger antenna system, massive MIMO, than to have multiple cell sites with new millimeter wave technologies. So lesson learned, that's also the direction that we see for 6G.
Right. But when I ask telcos in Japan, so they all say that they would like to use that for hotspot, like millimeter wave, not like area construction. But I wonder there is inconsistency between what the vendors are talking about and then what the telcos are interested in.
Yeah. So we do talk to providers in different parts of the world, and the low deployment cost is always upfront. And in many parts of the world, the upper mid-band does resonate with operators that we talk to. Indeed, the alternative is to stay with the current mid-band and then have indeed the hotspot deployment with 5G millimeter wave. It is probably geography dependent, demographic dependent, so we'll maybe need more planning and techno-economic analysis to determine what is best. But we largely see if you can do it from existing cell sites, you do it from existing cell sites.
Thank you very much. Let me ask a very quick question, another one. So I'm excited about this AI native AI interface. That's a great idea and a 30% gain. But I'd like to ask you about the commercial viability of this technology, because apparently you have to put a lot of power in this AI calculation, and the gain that you get is the 30%. And if you have any comment on that, you have outlook for commercialization for this technology? We have to develop a chip if we want to go for that.
So indeed. So we actually already invest in research in SoCs that can do these kind of AI inferences. Not for the first generation of 6G, but say maybe for a second release or so of the equipment, we will have new ASIC technologies that use a combination of analog and mixed compute and such things as compute in memory to really get to the most power efficient processing of the AI signals. So in all fairness, likely not for the first product releases.
Thank you very much.
Thank you. Okay. では2列目の中央あたりの方になります。
Yeah, thank you, Peter. This is Mitch Zheng. I'm the vice chair of the applications working group of NGA, and thank you for the presentation. My question is actually kind of continue from the previous speaker. That is the use of AI. Is AI a friend or foe? Right, a friend to help the 6G, or is a foe that may defer our deployment of 6G? The main reason I have this concern is that when we talk about the AI, we seldom talk about the cost to deploy AI. So in your scenario, the connectivity, the network, we can see the wonderful results. AI make the RAN be more efficient. That part is great. But on the other hand, once we start massively deploy AI, then the computing load we impose on the AI network and also application there on the data center, they will inevitably increase the energy consumption, which kind of against one of our targets for 6G. So I'd like to pick a brain on this one. Thank you.
So AI is definitely the defining technology that justifies a new generation of networks. Most prominently for deployment, the automation of the network. The AI editor phase is, as I already answered in the previous question, is maybe not for the first releases, or not to the extent as I described it here, completely native. Maybe more for dedicated functions in the first releases. AI as a friend, AI as a foe. We will rely on AI for critical decisions in the network, so it needs to become reliable. It needs to become what we call responsible. The AI needs to be fair, and it needs to be also secure. So that is an important area of research, to make sure that we have responsible, safe, accountable AI, accountable that then also allows for allocation to different actors. AI also as a tool, AI to detect anomalies, for instance, and then AI as a threat, because AI can decrypt and insert malicious behavior. So you have a new cat and mouse game that you also need to understand better.
Thank you very much. では他にご質問ございますでしょうか。ご質問は日本語でも結構でございます。Any other questions? Okay. ではこちらに一番前の方です。はい、来ます。
Thank you very much, Peterson. And yes, related to the previous question, yes, I'd like to know your views on the expectation on the balance between the energy efficiency and improvement of the radio performance, data rate, and the capacity. In principle, yes, it's a little bit difficult to improve both drastically. Yes, one of the examples should be AI. Yes, AI consumes the energy consumption, and maybe massive MIMO consume the power consumption. So what do you think about the future technologies to improve both energy efficiency and radio performance? Or what kind of balance need to be considered? Do you have any views on that?
Yeah, thank you for the question. Indeed, AI can also be a tool to optimize the power consumption, anticipate traffic needs, I explained the antenna muting, for instance. That can be something that you automate with the help of AI, the power backup schemes and such. So AI is also a tool that can help us in the creating more energy efficient networks, also the efficient allocation of compute in that cloud continuum. I think, as already said, the first generation will likely be more the classical compute capability, but there is progress in ASICs that is really promising to enable those new AI capabilities, both for network functions in the cloud as well as at the base station.
Thank you. では他にございますでしょうか。他にご質問ありましたら挙手をお願いいたします。Any other questions? No questions? OK、それでは、質疑応答以上とさせていただきたいと思います。なお、この後18時30分からの夕食会でも、ベッター様と交流いただけますので、もし個別でご質問したいことなどがございましたら、ぜひ夕食会で意見交換をお願いいたします。Mr. Vedder will be joining us for the party.After the conference. So if you have any individual questions, please feel free to ask them at the dinner. We'd like to conclude the Q&A session. Thank you very much, Mr. Vedder. We are now preparing for the next presentation. Please wait for a moment. Thank you for waiting. The next speaker is Mr. John Sumi, Senior Vice President Engineering, Global Head of Wireless Research, Qualcomm. Mr. Sumi, please.
Well, thank you very much for having me here. It's certainly my pleasure to be talking about 6G at this conference here in Tokyo. And after so many great discussions on 5G and seeing the power of the deployment in Japan on 5G, it's really exciting to be already exploring these future topics as part of the Beyond 5G conference. When we look at the role of compute, and even as the last few questions showed, a huge amount of interest these days in the role of artificial intelligence and AI. And we're very familiar now with the power of AI in the cloud. And what's also incredibly exciting is the fact that AI is making its way into many types of on-device compute. So for example, the computer even in this laptop or in my smartphone already has its own CPU and GPU and neural processor. And this is also shifting a little bit the center of gravity of processing. And this is important both from a scale standpoint, but also from a new application, recognizing that a lot of the value in connectivity is created at the edge of the network across devices, and then it's that interaction between the devices and the network that helps bring many types of value to the system. So this hybrid artificial intelligence really also is an exciting part of this journey as we move from 5G into 6G time periods. And if we look at the role then of edge devices, it's also about the expansion beyond the smartphone. So whether we're looking at connecting automotive systems, consumer IoT, IoT edge networking, or even industrial IoT. So there's many different types of devices that are a part of this cellular system expansion. And one of the exciting promises of 5G that it was a unified connectivity platform. So as we look for value creation within 5G, it's about the mixture of new types of services and new types of devices, and recognizing that the ever-increasing capabilities of these devices really have to be combined with the possibilities of more improvements in power consumption and energy efficiency, and then also in the battery life of many types of devices. So this era of IoT and connected devices is really continuing to evolve, and it's opening up new possibilities for the cellular ecosystem. If we look at technologies, and it's really exciting to be thinking, here we are talking about 5G and 6G, and the reason for this 10-year cadence. I know this often gets discussed in the industry. Is 10 years an arbitrary number? The reasons it's important is there's both a supply side of technology and a demand side for new use cases and applications. And so the supply side is always increasing as well. If we look at the era of cloud computing, the era of AI, but then also the advancements in new types of services and applications. And so this 10-year time period is also very important because it forces us to take a step back and to think a little more longer term and basically to think in a historical context as we project forward. So what is the world going to be like in 2030 when 6G is initially deployed? What is the world going to be like in 2040 as we're starting to think about the next generation after that? So that requires a lot of imagination, and it's not about perfectly predicting the future. It's about ensuring we're designing the most capable system, a system that can continue to evolve, and a system that can meet future applications, even as they're unpredictable when we design the original system. So that really underscores the importance of focusing on the right metrics, making sure we're improving the cost effectiveness of deployment. The fact that the OpEx and CapEx really have to be a focus of improvement into this efficiency. So the technology steps that have been made in the last 10 years will enable us to design 6G in a different way than 5G because the tools are different. And we really do have to fundamentally focus on that value proposition of connectivity. A device that's not connected is a really hard way to create value, which is why almost every single device we're aware of these days is connected. And more of that connectivity is going wireless. So we also see that continued expansion into industrial activity, into that overall role of human productivity, taking this communications technology and merging it with evolving compute technology. And the other point then is this perspective of where are we at in terms of the early stage of 6G, and the fact that 5G itself is in the commercialization phase as we look at 5G Advanced now, releases 18, 19, and 20. And so it's this perspective that we're starting to think about how do we construct the 6G system? Are we bringing the right players into the 6G ecosystem? And then also, are we starting to think a little bit about what are some of these lessons learned from the 5G deployments? How can we make sure we're focusing on the right steps forward so that these steps are as big as possible, so they give us the most gain, but then also so that they allow us to have the longest runway to monetize the 6G system. So there's a lot of technical opportunity and then also a lot of optimization that needs to happen to ensure we're focusing on the right sort of technologies. If we look forward then to a lot of different technologies, what's interesting is the role of the foundations and then the role of where we put these tools together. People often say, oh, is 6G going to use OFDM? Is 6G going to have MIMO? A lot of these things are very clear, that we will absolutely be using a lot of the core technologies we innovated in 5G. But at the same time, we're also going to really have to bring in some of these new advancements. So how we use new surfaces, how we use new bands, how we bring AI into the air interface. So it's also just really interesting that as we look at the technology evolution, we recognize that things are building on top of itself. The networks are continuing to evolve. The legacy devices are continuing to operate. So we're really putting together a more complex ecosystem of technologies. And it's that point of the embarking on 5G Advanced is really about making sure we can realize the value of those 5G investments. So we're not talking about 6G today because we think it's time to stop evolving 5G. It's about the fact that 6G itself needs to build on top of that 5G foundation. So we absolutely have to make sure that 5G is continuing to get deployed and that the new bands are bringing that value. So the combination of 5G, 5G Advanced, and 6G really are on a continuum, even though we obviously have discrete goalposts and markers as we look at the standardization and the priorities. So that's one of the most exciting things about being in this industry is the maturity that's required to combine these long-term technology vectors with the changing business realities. It also underscores the importance of conferences like this where we're exchanging a mixture of ideas from many different types of companies so that we can look at, are we addressing the right problems in the right order? A good example of that is the sort of optimizations that went into 5G itself. We like using this plot because it shows so many different types of use cases, whether it was adding NTN for terrestrial to satellite communications as part of Release 17, or the expansion of 5G itself into reduced capability for lower tier IoT devices in Release 17 and enhanced RedCap in Release 18, or even bringing augmented virtual reality to make sure it's as efficient as possible on the cellular network. So that initial 5G Release 15 deployment evolved into Release 16, 17, 18, and 19. So we're about to embark on Release 19, and it really represents the whole industry coming together globally. It's great to see so many people from different countries here today because it really is a global ecosystem that helps us continue to drive cellular forward. And it's one of those things that enables us then to work with operators globally and understand the different priorities so that we can focus and design the 6G system. And if we look at some of the key different vectors, what are we looking at? Well, one of them is the core technology advancements. This really is what we call the supply side. What is different from a technology perspective? What is different from an academic perspective? The other thing, though, is what are some of the new requirements getting put on the system? What are the priorities across governments and across regions? And so the environmental, the social sustainability, those are continuing to be really important topics when we look at the role of the communication ecosystem. The value of that cellular ecosystem really needs to meet the needs of many different markets. It's not just about higher data rates and incredibly expensive devices. It's really about the fact that we have to bring coverage to more people and do it as cost effectively as possible. And the other thing is then bringing in new user experiences. So how are we going to be able to transform new fields or transform human productivity in hospitals and schools and factories? Well, that requires us as engineers to combine the interesting technology components and marry that with the business realities of what's going to actually get deployed. So this is also a very interesting point that we have to look at the different components of it. And when we look at the global ecosystem, as mentioned in some of the other talks, we have the reality of what is happening in North America, Europe, and Asia. So the role of the academic research, the role of these bodies where we're able to exchange information is incredibly important for that global momentum because it helps us put the pieces together in different ways. It also helps us ensure that we're looking at the priorities in the right way, recognizing that 6G is not going to be deployed in one country, it's going to be deployed in so many different countries that we really have to incorporate a broad number of requirements. So that's the other part of that ecosystem reality, and making sure that we're getting all of these different systems together. If we look at the use cases, this is also an exciting challenge for us. So we work with many of our different customers to understand what are the pain points they're experiencing now. How does that relate to compute? How does it relate to communications? And how does it relate to the reality of the new user experiences? On this application then, we can see augmented and virtual reality really as an excellent example of something that's continuing to change. Every day there's a new requirement. Every day the ecosystem is also evolving in terms of the different players. If we look at the role of taking cellular into new types of enterprise applications and improving productivity, there's a huge number of different requirements. And so the question is, what do we really need to improve under the underlying cellular communications fabric? So collaboration, even as we're looking for ultra wide area connectivity, the perspective of making sure that 6G is going to bring value in dense deployments, but also in wider area IoT applications where coverage is the most important metric and the data rate is much lower. Or even how do we bring 6G into interesting enterprise applications like configurable factories and hospitals? So there's a lot of exciting challenges in front of us as we're putting together that technology components with the business components. And what's nice also seeing some of the other talks today is this convergence on some of the core priorities. So many of us are very familiar with the triangle of 5G, the mobile broadband, the IoT, the critical communications. That was a great way to ensure we were challenging ourselves and designing a system that could extend to different applications. As we look at 6G, it's also about ensuring we're incorporating more inputs into that process. That we're also looking at some of these more immersive platforms and services. And also that we're bringing in this huge focus on energy efficiency and looking at how we can bring in a more futuristic version of spatial perception. Where is that technology going to be in 2035? So if we kind of break apart these KPIs, then on the engineering side, we now can understand the challenges more concretely. So absolutely, the communications core challenges, data rate, coverage, reliability, these are the things we've been optimizing since 3G, but we have a more powerful tool chain to do it into 6G. Qualcomm's also heavily focused on bringing AI into the air interface, and the on-device AI combined with the AI in the network enables many interesting applications. The focus on resiliency and making sure the 6G system is designed for the realities of the world 2030 to 2040. That means we have to understand new security frameworks, new types of attacks, and make sure we're building that resiliency into the system. And sensing is also going to be really interesting. So we have the waveforms for communications, and then we have the waveforms for sensing. So the role of integrated sensing and communication means we can use some of these new frequency bands to better serve types of sensing applications. And sensing monetization is always changing. The ecosystem that can benefit from a digital twin is changing all the time. It's in its early stages right now. So as research scientists, we're really looking hard at what are the sensing technologies that can be incorporated into the cellular system. How does that combine with different types of devices, form factors? So very low power IoT, even ambient IoT systems where there's not a battery, there's just a capacitor. Those are examples of stretching the challenges for the 6G waveform to make sure we're serving an interesting number of use cases. And then also looking at that power consumption, the energy efficiency of operating the system. That goes hand in hand with how we're slicing the data, how we're looking at the core versus the RAN, how we're looking at the radio units versus the central unit. All of those optimizations are important to make sure we're bringing as much power efficiency as we can into the network. So if we look at the path then and the key vectors, one of the important things is aligning ourselves along these core mission statements, the AI native end-to-end communications, the focus on new spectrum bands, whether it's 7 to 15 gigahertz, or also bringing new designs into millimeter wave, bringing new designs into not only sub-6 gigahertz, but even low-band FDD systems. How can we ensure to take the best technologies we can develop to improve the power of the low-band FDD system, because 6G is going to be deployed in legacy bands in addition to being deployed in new bands. So that means we have to bring frameworks to allow that 5G, 6G joint operation, to allow that smooth migration from 5G spectrum into 6G spectrum. And the communications resiliency is another key focus area. We had a lot of focus in 5G on high data rate and high reliability, low latency communication. So the question is, what would we do differently in 6G? It's about really understanding those threats and attacks more differently. So then we break it apart and say, well, if 6G is going to be, after all, an air interface, what are the key requirements for that air interface? So the spectral efficiency. Every day we're reminded of the importance of using the spectrum as efficiently as possible. Even the outcomes of WRC 23 were very positive for the IMT industry, but at the same time we know we have to use spectrum as efficiently as possible. And we're able to use it more efficiently than we were in the past. So what are ways we can improve the spectral efficiency in legacy bands? And at the same time, design new techniques for higher frequency bands. And so this is a way of bringing in the most advanced technology and saying, what sort of processing can we do in 2030? What sort of processing can we do in 2035? So that's an interesting reality of the challenge of designing for this moving target of where technology is going to be in the future. And so if we look at modem chipsets, where Qualcomm puts a lot of focus on ensuring there's ecosystem and a wide number of device types, we're always focusing on that power efficiency and also the efficiency of delivering communication across different bands. So it's a huge challenge as we're designing all the way from the radio to the baseband and ensuring that we're bringing that together. And then sensing and communications is an inherent challenge for not only how we design the waveform, but then also how we multiplex the hardware. And so we put those things together and we say, yes, we can design a new 6G air interface for communication between networks and devices, but it's also about how we put the ingredients together. And AI and ML is a good example where we can move from having smart base stations and smart devices to having more collaboration, cooperation between the devices and the network, what we term cross-node machine learning. Well, we feel 6G is also going to take that to the next level. As both the prior talks showed, this is a huge focus area for the industry. Hundreds of researchers are focused exactly on this problem. So AI is a tool, AI is a use case, AI is an opportunity, and also AI is something that we know can result in new threat attack surfaces. So AI is a huge focus because it's one of the core technologies that's evolving and changing incredibly quickly. And so how it intersects cellular is part of the challenge of designing the 6G system. What's exciting about digital twins is this recognition that the value of understanding the physical world and the value of understanding the virtual world are starting to intersect. We can better optimize systems when we're working in the virtual world. At the same time, the sensing and the integrated sensing communication is making us think differently about the physical world. So these digital twins are incredibly relevant, not only for connected factories, but also for the whole role of augmented and virtual reality. Or if we think about a smart city and we look at the role of vehicular communications, it's tied right into that network and device intersection. So we're really excited about the role of spatial compute, not only from our XR business line standpoint, but also how does it map into how we design a 6G system? How are we designing it so that digital twins can be more economically realized as part of 6G? And many of us in this room are probably going to be in Barcelona next month, and that's another example of where these technologies come together. The whole world descends onto the stage, and a lot of different discussion points of what have we made better in 5G Advanced? What are some of those example points as we head into 6G? So if we're looking at 5G Advanced, if we're looking at 6G core research, these are some of the key demonstrations that we'll be having at the show next month. So thanks for giving me this opportunity to mention some of them here. But it's something where these technology demonstrations combine proving feasibility with exploring the business opportunity. So it's about understanding what we can do differently and then also incorporating feedback globally from different account teams and different teams that are also exploring these technologies. So it's a really exciting time for cellular as we're about halfway through the 5G system. and getting ready for the next 5 years where we're going to embark on standardization and targeting that deployment around 2030. And so when we put those different ingredients together, it's about combining that technology evolution with continuing to challenge ourselves in constructive dialogue about what we can do differently and what we can do better and how we can bring more value into the overall system. So very happy to take any questions now, and thank you again for the opportunity to speak here.
Thank you very much, Mr. Sumi. ありがとうございました。それでは質疑応答に移ります。ご質問のある方は、挙手をお願いいたします。はい、それでは一番前の。
Yeah, thank you, John-san, for a very excellent presentation. Maybe Professor Nagao has many questions. Before asking questions, I would like to ask a question to you. Yeah, as you said that maybe many new features, functionalities, or solutions will be added even in the 5G, and then we will have more new features in the 6G. On the other hand, my question is, what do you think about the backward compatibility for the 6G? Operator point of view, of course, we want to introduce the new generation system 6G with the backward compatible manner for the smooth introduction of the 6G. But if the 6G new features can have enough gain, we can allow the non-backward compatible manner. Yes. But at this moment, yes, it's a little bit tricky to have a very big gain in the 6G. That's my kind of thinking, concern. And also, new potential features of the 6G could be introduced with the backward compatible manner. What's your current views on the non-backward compatibility? Non-backward compatible manner 6G introduction is needed or not needed?
Yeah, so that's an excellent question, Nakamura-san. And the point is that the forward compatibility is incredibly important. So when we look at the 6G waveform, we do think it will be a non-backwards compatible physical waveform. At the same time, the power of carrier aggregation and even the role of dynamic spectrum sharing. So if we combine CA with DSS, and we term that MRSS for multi-radio shared spectrum. So that will enable a more dynamic interaction between 5G and 6G. And so the hardware that gets deployed in 2030 will be capable of doing 5G and capable of doing 6G, but the percentage of 5G to 6G in a time frequency allocation standpoint can smoothly change. So we absolutely feel that the smooth migration of legacy bands so that the 5G investments are realized. And at the same time, we are optimistic on the spectral efficiency gains of the new waveforms. So the accumulation of technologies in the last 10 years, in our view, will make release 21 significantly better than release 15, and obviously much better than release 8 when we look at the original LTE. And so if we go back even to some of the FDD bands and we start looking at the advances, then we can build a more powerful non-backwards compatible waveform. But we then often introduce the term forwards compatibility into the language because it is going to be compatible, but it will not be just a 5G evolution only. Yep.
Okay. Thank you very much. And Professor Nakao?
Thank you, John. I have only two questions. So the first question is so about an IoT chip, because we have NB-IoT and LTE Cat M1, and those are not, in my opinion, those are not very successful yet. And you are talking about Red Cap. And do you have, can you tell us the outlook of Red Cap, the future of the Red Cap, and what's the, the commercial business opportunity about that? This is my first question. And the second question is rather strange maybe to you, but so Qualcomm as a company is very successful globally, in my opinion. Well, I think lots of people here believe that way. But do you see any competition that might, you would fear in 6G business market? Do you foresee any like challenges in Qualcomm business? I'd like to hear that.
Okay, well, thank you very much. So I'll take the first question first. So what's interesting with IoT, and it goes back to the 5G triangle, when we looked at, did we really need in the very beginning of 5G to introduce a new version of NB-IoT or eMTC, which were 4G technologies? And the answer was no. We said we can actually leverage those technologies, but combine that waveform to the 5G core. And I think one of the lessons learned about the 4G, 5G migration was that the non-standalone variant had some pros and cons. One of the challenges was that it delayed the deployment of the 5G core for some of the operators. The promise of cellular and IoT communications, it's about combining wide area coverage and not very high data rates. So the data rates are very achievable, but it's really about coverage and deployment, but more importantly about what is the service being offered. Because you're not charging that by the kilobyte, you're charging it by the use case. So for the operators who have been exploring with IoT, it is a very long cycle. The consumer cycle we know is roughly every 2 years or so in terms of getting a new device because of many, many other changes within the device in addition to the wireless part. For IoT, I think we all learned some lessons that it is a longer time period. Industrial IoT is in particular an example of something where the ecosystem needs to absorb that technology and they do not want annual cadence of refreshes. So for NB-IoT and eMTC, those data rate targets are lower than was what focused on for RedCap. So even for Qualcomm, we announced the SDX35, a Snapdragon product that's focused on RedCap. And it's an example where, from our view, the sort of data rates with RedCap, 100, 150 megabits per second, it's very compelling for a lot of interesting applications. And it's not about having a peak rate. So even as one of Peter Vedder's plots showed, when you turn off the system, you also start saving power. So having a higher data rate enables more bursty, efficient communications for that energy per bit. So that transfer of information can be done efficiently, even if the data rate is higher, because you're turning it off. So in our view, RedCap is an exciting technology. Operators are getting their plans together, but RedCap also requires the 5G core. And so that's not immediately obvious to everybody because it's a waveform, a bandwidth, an antenna configuration and capability, but it also leverages that 5G core. So as the core networks are evolving from NSA to SA, from non-standalone to standalone, that increases the market opportunity for RedCap. And we don't feel that in 6G we have to immediately design a new low-tier IoT. But what is interesting is that we would look at technologies about sensing and communication and ranging, then the value opportunity for IoT really does include a lot of these industrial applications or logistics applications. And it brings in positioning and sensing and ranging in addition to very low data rate communications. So we are excited about the future possibilities of ambient IoT, and that's why it's being studied, even in release 19. But we think it's important that as an ecosystem, we really focus on absorbing the technology learnings and in planning the business strategy. And I think the second question obviously was a little bit more of a business question, so I'll have to answer it, generically in this large audience. But the point is there's always huge amounts of evolution in the cellular ecosystem and also many large players providing interesting solutions. So in our view, what's exciting about cellular is that ecosystem has continued to expand in terms of the different types of device types, the different sort of applications. And so from a global standpoint, we're quite excited about how cellular is evolving. And then even as a company, we look at the role of compute, the role of IoT, the role of automotive, the role of XR. And that's all interesting opportunities that are different than the smartphone industry. And so the smartphone industry is incredibly powerful and important, And at the same time, the cellular ecosystem value, it's about also extending it to some of these other applications. Yep.
Okay, thank you. では、他にございますでしょうか。他にございましたら、挙手をお願いいたします。Any other questions? No questions? Okay. はい、それでは以上で質疑応答終了とさせていただきます。This concludes Q&A session. Thank you very much, Mr. Sumi.
Thank you.
Thank you.